Lab 2 for Physics 2212, and it's on magnetic fields of a bar magnet. To introduce the lab, the main purpose of the lab was to determine the magnet's magnetic dipole moment and then to use it to visualize its magnetic field. And then we also compared the off-axis computational and experimental magnetic fields. The main models and fundamental physics principles used were the Biot-Savart law, the magnetic dipole moment, and then we talked about distance dependence. The main results are shown where the magnetic dipole is below 2.2258 amperes times meters squared, and the off-axis comparisons are below. And then the formulas for these main fundamental principles are shown on the right. The top formula is just the standard Biot-Savart law, and then the one below it helped us find the dipole moment, but by rearranging it for the experimental computations. And then the formula below that was what we used in the computational model. And then the two formulas on the bottom was how we translated our experimental data using distance dependence. Our initial conditions were shown on the left. That is how I arranged my setup, so that way the magnetic field in the x direction would be 0. And then the system was the magnetometer, and the surroundings was Earth and the bar magnet, and then the procedure is shown on the right. So first we did everything on axis, so we went through and calculated the magnetic field of the magnet at a set amount of distances, and then this is shown on the right, and it kind of plotted it together, and we were able to get a formula that we could pull calculations from. And then after we did all of that, we talked about the off-axis experimental data where we used a set distance and then calculated d and then used that to find the net magnetic field. This right here shows the calculations that I did. These are the distance dependence formulas that we were talking about, and we were just able to manipulate them and rearrange them in order to solve for mu. We also used the slope in this line of best fit formula to help to fill in these different variables. And these were the questions that were asked in the lab that are answered as shown. Next up was coding. So first off, we had to create the magnet at the origin, then we created the function for the magnetic field, then we visualized the magnetic field, and then lastly we visualized the magnetic field at the 45-degree angle of the off-axis. And then my graph is shown, or my model is shown on the right. The comparisons for my data are shown below. The off-axis experimental field for my experimental model was 1.63 e to the negative 4 teslas, where my computational model was 5.0572 e to the negative 5 teslas, and we'll talk about that in a second. So the reason that I believe that my two models don't align identically is because of a slight change in my BZ Earth approximations. When I went through and did this lab, I did it strictly based off the instructions and filled out the spreadsheet later. So the instructions initially just said to take account for the Y components, so I didn't originally go in and find the BZ components for this specific step. But I was able to have a graph of all my data saved, so I went through and approximated the data through the graph, but it might have had some room for error, which could have associated with a difference in degree of magnitudes. And then as well, my magnet was chipped. What if? In the experiment, if you oriented your setup so that it would compensated for magnetic north, what would have happened if you wouldn't have done so? I would believe that the results would be less accurate and inconsistent, as you would have no baseline to guide your measurements. We also wouldn't be able to isolate the magnetic field of the bar magnet if we knew the x component for Earth wasn't 0. And then for this Y question, I think that if they were stuck together end to end, their magnitudes would increase. Nothing would cancel out, because in order for them to be stuck together, the positive and negatives must meet in the middle, aligning the directions of their magnetic fields, which would thus increase their magnitudes and then also increase the magnitudes of my measurements. Thank you.